So for that particular thing, what you have to do is you just have to form the carbocation. So if you are going to form the carbocation, just like it's a Br, so Br is the leaving group. So I told you that about the leaving group, about the nucleophile, I'm going to tell you in the substitution and elimination part. In that particular chapter I'm going to tell you, but in the particular Br, chlorine, iodine, these all are very good leaving groups. So Br is a leaving group. As the Br removes, there is a generation of the carbocation. As the carbocation generates, so what happens, this particular carbocation, I will draw here this. So this is the carbocation, I must say this is the carbocation. So from this particular carbocation, this is stable, but the carbocation on this particular thing is more stable as compared to this. You can form this as well, but you have to do a competition. You have to do a competition before the products. Because this is a tertiary, this is also a tertiary carbocation, this is tertiary, this is tertiary. So you have to prioritize the carbocation which is forming on the ring as compared to the carbocation which is not forming on the ring. Because the carbocation on the ring is more stable. So you have to prioritize this with the rearrangement. Sometimes you have to prioritize this. So which you have to do a prioritize. This will depend as many as questions you practice and some specialized reagent that I am going to tell you in the reagent part. Now, what you have to consider here is one path rearrangement can occur through the hydride shift. So, what's the meaning of this is you just have to follow the arrows. So, if I'm saying there is a CH3, there is a CH3, there is H, and there is again CH3 with a positive charge. So this is 1, 2. This is a secondary carbocation. Okay, so this is a secondary carbocation, and if this particular methyl group shifted, then there is a formation of the tertiary carbocation. Tertiary carbocation is far stable than secondary, which is more stable than primary carbocation. So this is the order of the stability of the carbocation. So as the tertiary carbocation undergoes the tertiary carbocation formation from the secondary carbocation, there is a transition state, and this is most important part in organic chemistry to understand the formation and the arrangement of the transition state as well as the intermediates. So you have to do this. So this particular hydrogen goes here, and this particular hydride shift can be there. If hydride is present, sometimes there is methyl shift. Hydride shift or methyl shift, you can do both. Whichever possibilities there, do that. And whereas the migratory aptitude of hydrogen is more as compared to CH3. So if there is hydrogen, do the hydride shift, and if there is no hydrogen, there is 2 methyls, so you have to do the methyl shift. Suppose if we have CH3, so you will do the methyl shift, but there is hydrogen, so you have to do the hydride shift. I have explained you both the cases for methyl as well as the hydride shift. Next, some examples of allowed hydrogen arrangements are C. In the primary carbocation, if hydrogen moves on this side, there is a secondary. So from primary carbocation, I am getting the secondary carbocation. Here I have the primary. So from the primary carbocation, I am getting the tertiary carbocation. Here we have a secondary, and here we have the tertiary. So from less stable carbocation, we are forming the more stable carbocation, and that is the most important part of the organic chemistry. From less stable things, you have to move your pen and you have to move the arrows in the most stable sides. So this is the very important thing that you have to consider here. Always remember that carbocations with the same substitution pattern can rearrange in a resonance stabilized carbocation. Suppose if we have this particular secondary carbocation, if this hydrogen comes here, so this is stabilized by resonance. This carbocation is stabilized by resonance, so we have to favor this. We have to favor this particular structure. Both have done and undergo a hydride shift, but you have to prioritize this for the reaction mechanisms, because if reactant is converting into a product, you have to use this intermediate. You have to use this intermediate. So in the intermediate, you should know about the rearrangement and the hydride and the methyl shifts as well. Now, rearrangement can accompany the reaction in SN1. So, SN1 in which the carbocation is mostly formed. So, this I will explain you in detail, but here I have just explained you for the sake of your convenience, because the leaving group leaves. As the leaving group leaves, there is a formation of carbocation. There is a formation of secondary carbocation. That secondary carbocation leads to the formation of tertiary carbocation here. The tertiary carbocation by the hydride shift. Tertiary carbocation is formed by the hydride shift. So as the tertiary carbocation is formed by the hydride shift, there is a nucleophilic addition. So the nucleophile add, and there is a nucleophile addition. So a nucleophile is bromine. So what happens as the carbocation forms here? So addition of nucleophile. So nucleophile is not Br minus, nucleophile is H2O. So there is a competition between H2O and Br minus to act as a nucleophile, but the water always wins in that, and the H2O added, and here H2 OH2 plus. So there is a removal of H and there is OH, and there plus में H3O plus in the presence of Br minus can be written as HBr sometimes. So this is the complete SN1 mechanism that is going to happen. So first this step is first step is removal of leaving group, formation of secondary carbocation done with the hydride shift. After that there is the attack of the nucleophile, that is water, and as the water, suppose I have this CH2 plus and I have written it H2O here. So H2 attack on this side. So what happens when the H2 attack on this side? We can written as CH2 and OH like this. Okay, and we have to add a plus sign. So in this way we are going to write. So I have to write index. Okay, so we have a plus charge here. So what we are going to do is we have to remove this. So we have another H2O with us. So it will remove this, and there is a formation of H3O plus. There is a formation of H3O plus CH2OH like this. So this is the way in which the H2 attacks and the formation of H3O plus will happen, and the formation of alcohol Now next thing is deprotonation. Deprotonation, this is the step of the deprotonation that I have told you. This is the deprotonation step that I have told you. This is the deprotonation step that I have told you just now, and the final product is SN1 with the rearrangement. So in this way you are going to do the carbocation reactions. So there are some another reactions you can try. You can try to draw the mechanisms, because if there is a Br and there is CH3OH, so what will happen? Br will remove, there is a positive sign, and again there is a hydride shift. As the hydride shift here, CH3OH, and in this particular CH3OH alcohol, this ROH. So RO minus will act as a nucleophile, and there is a attack of the nucleophile here. So similarly you can undergo with these reactions as well. Now consider, so here we have the leaving group, so we have to leave the leaving group. Leaving group leaves from this particular side. There is a formation of carbocation. As there is a formation of carbocation, the ring will expand because the carbocation is adjacent to the ring. When the carbocation is adjacent to the ring, the ring expands. Always remember that the ring will expand. When the carbocation is adjacent to the ring will expand to the 5-membered ring, and there is attack of the nucleophile. H2 is a nucleophile. It will attack here. The deprotonation step will happen, and after the deprotonation you will get to a product. So this is the way in which the loss of leaving group, alkyl shift will happen, because the carbocation is just adjacent to the ring, and when the carbocation is just adjacent to the ring will expand. As the ring will expand, there is a 5-membered ring. Water will attack, nucleophile will attack. After that there is a deprotonation step, and you will get your desired product. So in this way the reaction is going to happen in the organic chemistry. You have to do this. So now we are going to do this. Resonance. As I am saying about resonance, so what you have to do in the resonance here is, as the number of the resonance increases, the stability of carbocation increases. I have told you to prioritize the resonance as much as you can. So it's a very important thing that you have to consider, because the stability of the carbocation which is nearest to the resonating group is must. So if the carbocation can be formed around the resonating groups, that is most important, because the greater the number of the resonating structures, the greater the stability of the carbocations. Because these are some steps, or these are some points that you have to remember. You have to understand this first, and after you practice these things you can able to remember this thing. So the greater the number of the resonating structures, the greater the stability of the carbocation. Always remember that the delocalization of a positive charge. Suppose I have a CH2 group here, and here we have a phenyl group like this. So this is, I am talking about, this is a resonate. This is a resonating. This is the resonating stabilized carbocation. This is the resonating stabilized carbocation. So what you have to do is, this is the resonance stabilizing carbocation. So the delocalization of the positive charge causes the electron loss, delocalization of the charge causes the electron loss to decrease further and increase the overall stability, because in this way the stability of the carbocation increases and the structure that have the resonating structure are get stabilized. In this way we can say the carbocations are stable. So tricyclopropane carbocation is the most stable carbocation. This carbocation when connected with the three groups. This carbocation is stable because of dancing resonance. This carbocation is stable because of dancing resonance, and this concept is very important in organic chemistry. Like if anywhere this particular carbocation is wrong, just tick that's the most stable molecule ever in the organic chemistry. So because of the dancing resonance, this carbocation is stable. Why I'm saying so? Because this CH2 plus, this is stable. This is stable, and from this is more stable, and this is more stable. So in this way this particular carbocation is stable due to the dancing resonance. Now when we increase the substitution, so I have told you that tertiary is stable and secondary, then it's stable and primary. I have explained you various times why the hyperconjugation and inductive effect is there. Hyperconjugation can only be applicable when we have the alkyl groups, and inductive effect can be applicable when we have, for example, plus psi effect and minus psi effect when we have electron donating groups and electron withdrawing groups. As the distance increases, the inductive effect parameter decreases. So you have to consider this parameter also. So greater the hyperconjugation, higher will be the stability. So that's why the tertiary carbocation is more stable than secondary, and that is more stable than primary carbocation. So the carbocation stability depends upon aromaticity, mesomeric effect, resonance, inductive effect, and hyperconjugation. First of all, you have to prioritize the aromaticity. Second, you have to prioritize the mesomeric effect. After that, you have to prioritize the resonance. Then hyperconjugation, you have to prioritize the inductive effect. On these particular basis, you have to mark, you have to arrange the carbocations. In questions, usually sometimes these particular questions are arising, like arrange the following carbocations according to different electronic effects. So in detailed questions of this, I am going to explain you in that particular chapter, in which we are going to learn about all the electronic effects, all the resonance structures, ortho and para-directing groups. In that particular chapter we are going to learn in depth like how we are going to mark the stability. Now consider this hydroiodination of alkenes. So alkene is electron rich. I have told you alkene is electron rich. It's not visible. Alkene is electron rich. So alkene is electron rich. So if I am saying alkene is electron rich, what you have to do is you have to do it like this, because it's electron rich and it's electron deficient, because the iodine is electronegative. Iodine is electronegative, and if iodine is electronegative, it withdraws electron density from hydrogen toward itself, and if it withdraws hydrogen electron density toward itself, then this particular hydrogen is electron deficient. So from electron rich to electron deficient, the attack is going to happen like this. After that, there is a positive charge that develops on this particular carbocation, and the nucleophile will attack. So this is the way in which the which bond is forming, which bond is breaking. Just focus here. Which bond is forming, which bond is breaking, and I request you to please practice as reaction mechanism as you can, because it will help you ultimately. Next. We have a primary carbocation. It is converting into tertiary carbocation by methyl shift. Primary carbocation is converting into tertiary carbocation by methyl shift, or this. So both the carbocations are forming. Either we can move this way or this way. So you have to draw the possibilities as well. Draw as many possibilities as you can. Secondary carbocation is converting into tertiary carbocation. So it's a general mechanism. Wait, this X is leaving group, this X is leaving group, and if this leaving group is leaving, so there is the carbocation, and that carbocation nucleophile is acting. So we are going to get the structure like this with the nucleophile. So this is the exact mechanism. If we have X as a nucleophile, and the as the leaving group is there, and the leaving group if leaves, we have to minus the leaving group. As the leaving groups leave, so see, we have a leaving group. As the leaving group leaves, we have a carbocation with us. As the carbocation with us, we have a nucleophile that can either attack this way or this way. So we have a nucleophile. So in this way, the reactant is converted into product like this. The reactant is converting into product like this. So we have to discuss in brief like SN1 mechanism, SN2, SNI, E1, E2, where there are lots of mechanisms that you have to learn. So first of all, you have to become familiar with these things. Only then you are able to learn in depth meanings of everything. Thank you so much.